Okay, so today we're going to be talking about parallel circuits. What is a parallel circuit? Well, a parallel circuit is a circuit with two or more pathways. So when resistors are separated by a junction, the current splits, and that's a big idea here. So if we take a look at this example circuit to the right, we see I have a 9-volt battery here. As always, the current leaves the positive terminal and goes along the wire. Okay, it reaches this section here. This is the junction. Okay, in a junction, the current splits, and it's going to go down these two different pathways here. So you're going to get a current that goes down here, and you're going to get a current that goes down here. Okay, as this current travels, it's going to meet another junction. It's going to travel down this way, and it's going to travel through this way, where it continues on and passes through another resistor. This leads us to the idea that the amount of charge that enters this junction must be equal to the amount of charge that exits the junction. You can't have charge just sitting around here at this bend. This is what Kirchhoff's junction law states. The current that enters a junction equals the current that leaves. So if we have some current and it enters into this junction here, we can call that current in. It's going to be equal to the current that leaves. Okay, and the amount of current that goes through each of the wires following the junction, it's going to depend on the resistors that are attached to that junction. So let's formalize this and say that the current in is equal to the current out. This is a big idea when simplifying these circuits and answering any questions. The other key idea here is Kirchhoff's parallel voltage law. Now, Kirchhoff's parallel voltage law comes from Kirchhoff's loop law, which states that if you go around any one loop, the voltage drop must be equal to 0, or the change in voltage must be equal to 0. So what ends up happening here is if we start with this 9-volt battery, our electrons, or the current, has gone through 9 volts of potential, enters the junction, and it will cross across this resistor. Well, in order for the total change to be equal to 0, there must be a voltage drop of 9 volts across this resistor to reach 0 back here. But similarly, there must be a voltage drop of 9 volts across this resistor and a voltage drop of 9 volts across this resistor. It doesn't matter which path you take in a parallel circuit, they all have the same voltage. So the reason why this is because the currents are different. Okay, in series circuits, series resistors have the exact same current. It doesn't matter which, because they all have one path. But in a parallel circuits, the current's going to change. Now let's take a look at an example over here. This question states, complete the table for the following circuit. Now we can see here that we have a battery. Looking at the table, we see that the battery is a 24-volt battery, and we're going to have some current. It's going to leave the positive terminal, travel around, and it's going to reach this junction here. At this junction, the current's going to split into 3 parts: current 1, current 2, and current 3. But since we have a parallel resistor, or we have a parallel circuit, we know that the voltage is going to be the same across all 3 of these. In order for the change in voltage to reach 0, all of these 3 lamps must have the exact same voltage as the battery. So lamp 1 is going to have a 24 volts, lamp 2 will be 24 volts, and lamp 3 will also be 24 volts. So we can just straight away put all those numbers right here in our table: 24 volts, 24 volts, 24 volts. Now the next thing that we should be looking at is using Ohm's law. Now Ohm's law is what we really want to be using when we are breaking down these circuits. Ohm's law states that V equals IR. Okay? So if we know the voltage and the current, we can find the resistance, or if we know any of these two, then we can find a third one. Well, we know 2 pieces of information for each of the lamps and the batteries. So we can just straight away start using Ohm's law to simplify these. So if we take a look at the battery, well, we want to find the current. V equals IR. Well, we know the current is 24 volts. We do not know the current, so we're going to solve for that. And we know the resistance is 8 ohms. We can simplify this, and we can say that the current is going to be equal to 3 amps if you put that in a calculator or do the math by yourself. Let's go ahead and put that in. Now let's take a look at lamp number 1. Lamp number 1, well, we have 2 pieces of information. We're going to be using Ohm's law, V equals IR, and we know that the voltage is 24 volts, the current is 0.5 amps, and we're looking for the resistance. So 24 divided by 0.5, that's going to be 48 ohms. So the resistance in lamp number 1 is going to be 48 ohms. Here, well, we can use Ohm's law, but I want to use the junction law just because we have all the other currents. So we might as well get used practicing it. Okay, so let's take a look at lamp number 2. We said that the current going in, well, that's going to be equal to 3 amps. Well, 3 amps is the current that goes in, and that has to be equal to the current out. Well, the current out is I1 plus I2 plus I3. Well, I1 we know is going to be 0.5 amps. I2 is what we are looking for, and I3 is 0.1 amps. So, if we rearrange and solve for I2, we can see that I2 is going to be 1.4 amps. Sorry, 2.4 amps. And we can put that right into our table here. And we'd receive the exact same result if we used Ohm's law. The voltage divided by the resistance is equal to the current. And finally, for lamp number 3, we can use Ohm's law right here. V equals IR. The voltage is 24 volts. The current is 0.1 amps. And the resistance is the unknown. Put that in a calculator. We can see that resistance is going to be a whopping 240 ohms. And those are some of the main ideas about how to break down parallel circuits. Stay tuned for the next video where we look at combining series and parallel circuits in these simple situations.